Robert emailed me, please make sure to record, because he must live out in the middle of a farm somewhere, and they're just snowed in wherever that is. So
I was snowed in this morning. I was like looking for, I was like, come on, at least the delayed schedule, so I gotta get out of here. Nothing. Pissed me off.
remember last time our focus was to take our trig functions and no longer think of their domains being angle measures. We're now going to think of the domains of these functions as being real numbers. Okay, and we called them circular functions, all based on the unit circle. So bear with me for another class or two. We're going to stick with the concept of circular functions and domains of these functions being real numbers, and then we move away from that again. But really the focus of this class and the next class is to look at the characteristics of the graphs of our trig functions, the graph of sine, cosine, and tangent. And then if there's time, we'll look at the reciprocal graphs. But the introduction says that many things, and as you know, many things in daily life repeat with some type of predictable pattern. In warm areas, electricity use goes up, and in summer, use goes down, and from one year to the next, over and over and over and over again, you have that type of pattern occur. Attendance at the amusement parks increases in spring, declines in autumn, and that happens year after year after year after year. So they call these functions periodic functions, where you have that type of cycle occur over and over and over and over again. And as you're about to see, our trig functions, namely the sine and the cosine, are examples of those types of functions where we have a repeatable pattern within the graph that keeps happening over and over and over and over again. So the general form of a periodic function is a function f such that you can rewrite the function in this form, x plus n times p, where p is what we call the period of the function. Now our trig functions, we're not going to write them in function notation like that. We're going to leave them sine, cosine, and tangent. However, there will become a point where, yes, our calculator is going to do a lot of the graphing for us, but you're going to have to take, in certain instances, take the function that you were given and rewrite it, change the look of it, so that we can pick off certain values that tells us how the graph's going to behave. You're going to find out that, yeah, sure, you can graph it on your calculator, but still it isn't going to answer certain questions like what's the phase shift, what's the period, what's the amplitude of the function. Those you can quickly pick off from the equation after you rewrite it in a certain form. Kind of like, remember with the equation of a circle, if you take it and write it a certain way, you can pick off the center of the circle and the radius really, really quick. If you take a quadratic equation and write it in some other form, you can pick off the vertex really, really quick. Same thing's going to happen here. Now this should be reviewed to you, right? Last we spoke, we took the unit circle, and instead of the domain being the angle measure that's involved, dealing with the unit circle, our domain is now the length of this arc associated with whatever that angle would have been. Now we're just going to simply look at it in terms of the length of this arc, and then the x-coordinate of that point, wherever our arc stops, and that's just only applies to the unit circle, wherever that point is, then the x-coordinate is the cosine of that arc, or that real number, and the y-coordinate of that point is the sine of that real number, or the length of that arc. Okay? That's what we kind of talked about last time. Now, the smallest value of p for which the sine and the cosine functions start repeating themselves, as you know, is 2 pi. As we go beyond 2 pi, this whole cycle starts repeating itself again. The minute we go, we have this, just looking at the 4 quadrants, you all know that we go, in terms of sine, we go 0, 1, 0, negative 1, back to 0 again, so we just start repeating this whole process again. Same thing's going to happen for all the other angle measures. We have a pi over 4, 2 pi over 4, 3 pi over 4, etc. Finally, we get over here to 8 pi over 4. Once we go to 9 pi over 4, we just start repeating over and over again previous values as before. So 2 pi, one time around the circle, is what we define as being the smallest value, where after that things start repeating. from one trig function to the next. Okay. With the sine function, the domain's all real numbers, meaning you can plug any real number that you want into the function, and then what comes out of the function has to be between -1 and +1. So there's the domain and range of that function. Tying it into things that you may remember in the past, why is this a function? Because it passes the vertical line it does, right? And we say that the domain is all real numbers, meaning I can pick any real number on the x-axis. And if I go up far enough, or if I go down far enough, I will always hit the graph, right? No matter what x value I pick, you will touch the graph. However, the range will always be between 0 and 1, or -1 and +1. Now, what I want to tie together for you, because sometimes it's not as apparent here as, and we'll talk about the yellow rectangle here in a minute. I want you to make the connection between when we were dealing with the unit circle with now what this graph is that we're talking about as being the sine graph. And you can start seeing how this pattern starts repeating itself every time we go around the circle. So here we are, what's the sine of 0? Well, that's at 0. And then we go, what's the sine of 30-degree angle? Or what's the sine of this arc that would define a 30-degree angle? That's at 1/2. So we went from 0 to 1/2. And then here we are at 60 degrees, which is sine of 60 square root of 3/2. Convert that to a decimal. You're not quite 1 yet. Finally, when we get to the 90-degree angle, or pi over 2, the sine is 1, and we reach this point. Then if we start going on around, sine of 180 ends up being back to 0 again. So there we've gone from 0 to 1, back to 0 again, halfway around the circle. And now as we go from 180 degrees back to 360 degrees, that's going to complete to 2 pi. Now what happens? After 2 pi, what starts happening? This simply starts repeating itself for every time you go around the circle. You with me? See the connection between the circle and what you and I are going to consider on the right-hand side as being the graph of the sine function. And you're all okay and comfortable graphing that on the calculator, right? Getting that sine graph to show up. Making sure your calculator's in radians. You simply got to type in, find me the sine of this real number x. And you should do a zoom standard. And there's our function. Now, properties about the graph. Number one, it's continuous, meaning there are no holes, there are no start and stops. You could trace the graph continuously without picking up your pencil. The domain's all real numbers. X-intercepts. X-intercepts will always occur, and this is only true for y equals sine x, okay? This isn't other things that we're going to change later on, like y equals sine 2x, or maybe -3 times the sine of x. The yellow rectangle that you're seeing here only applies to sine x. X-intercepts will happen at any multiple of pi. So at 1 pi, we're back at 0, right? 2 pi, we're back at 0. 3 pi, we're back at 0. 4 pi, we're back at 0. So every multiple of pi, that's where the graph is going to cross the x-axis, so that means we got x-intercepts there. The graph is also symmetric with respect to the origin, which means for every point in quadrant 1, there is a mirror image point in quadrant 3, right? You're reflecting across the origin. And for every point in quadrant 2, it has a mirror image point over here in quadrant 4. That's okay. If you know it, great. If not, not going to hurt you. What I do want you to remember, though, which will help you with trig identities in a later chapter, when you have this relationship of being a symmetric about the origin, we call those functions, and you may remember this from college algebra, we call those odd functions with respect to the origin. And what's true about an odd function is these two are equal to one another. The sine of -30 degrees is the same thing as the opposite of the sine of +30 degrees. You have that relationship going on there. the sine of negative x is the same thing as negative sine positive x. You're going to use this equation occasionally when you're going to be proving trig identities. You'll just simply remember that, oh, okay, anytime I see the sine of negative x, it's the same thing as the opposite of the sine of positive x. Right? You're not giving me any feedback here yet. What's the sine of negative 30 degrees?
Negative sine 30.
According to what I'm seeing, right, it should be the same thing as the opposite of the sine of positive 30. Well, you guys know that negative 30 is the same thing as what? Positive how many degrees? 360 minus positive 330, right? So what is the sine of 330? Well, that's quadrant 4, right? And the sine's going to be negative in quadrant 4. So where are we at there? Negative 1/2. It's going to have a 30-degree reference angle. Is that the same as the opposite of the sine of positive 30? Absolutely. The sine of positive 30 is 1/2. We kick the negative sign out in front so you can see why this would be considered a true statement. That's it for those properties on the sine graph. Now, I understand, again, most of the graphing, and I expect you take care of most of the graphing on your calculator. However, there are certain properties about this graph that you're going to be able to pick off just by looking at the equation. Just bear with me here for a couple pages and we'll talk about those. Cosine function, again the domain negative infinity to positive infinity, and again the range is negative 1 to positive 1. However, what's the differences between cosine function and sine function? Now our x-intercepts are no longer multiples of pi, they are odd multiples of pi over 2. So that's what would cause cosine to equal 0. For example, if you let n be 0, 0 plus 1, 1 times pi over 2 puts you at pi over 2, and the cosine of that is 0. If you let n be 1, now we're at 3 pi over 2, so again cosine of that would be 0. So it's every odd, 2n plus 1 is a way of saying odd. Any odd multiple of pi over 2 puts you at a range value of 0. So those are where your x-intercepts are going to occur. Period, again, is also 2 pi, meaning every time you go through 2 pi radians, you're going to start repeating this same pattern within the graph. This graph is not symmetric with respect to the origin like the sine graph is. This guy is symmetric with respect to the y-axis. So for every point in quadrant 2, it has a mirror image point in quadrant 1. And for every point in quadrant 3, it has a mirror image point in quadrant 4. So those are not called odd functions, those are called even functions. And here's the relationship with an even function. The cosine of negative x is the same thing as the cosine of positive x. Same thing. And again, you'll use that more frequently in Chapter 5, dealing with trig identities. Okay? Now, between you and me and the online quizzes, the questions that you will be asked about graphing, I want you to use your graphic calculator, right? I don't want you to have to plot points and graph this stuff by pencil and paper. You know, some instructors would make you do it that way. We're going to use a graph. My word, you spent $2,000 for this calculator. Let's use it, for crying out loud, right?
Amen.
So, what I do want you to do right now is I want you to graph both of those, plain old sine x, and I want you to graph y equals 2 sine x. Graph those on the same grid, and I want you to tell me or think about what does the effect of that 2 do to our graph. So we got sine of x, and then we're going to graph 2 sine of x. And the one that you're seeing now is 2 sine x. So obviously, what's the difference between the two?
Magnitude.
Dude, we don't even know what that word is yet. You're exactly right. It's called magnitude. Do you already know that that's what it's called? Tom's like, what?
I'm not even listening to what he said.
Remember that sine x, right? Sine x, plain old sine x, what was the range? -1 to +1, okay? That's the highest point and the lowest point of the graph. Well, by us making that a 2, what happened? We now have taken the range from -1 to +1. Now the range is -2 to +2. So that's the big difference between it. We call that amplitude. What's the highest value? What's the low? How many units do you travel from the origin up or down to get to the highest and lowest point? We've changed that from a 1 to a 2. That's the difference. What are similarities that you see?
Periods are the same.
Periods are the same. We're allowed to say that word because we've already talked about it. With plain old sine x, it took us 2 pi radians to make a complete cycle. That didn't change. It still takes 2 pi radians to complete a cycle. So the only thing that we changed by putting that 2 there is we changed what's called the amplitude. Now you need to think of amplitude as being absolute value of the value that's out in front. What do I mean by that? If you're given y equals 3 sine x versus you're given y equals -3 sine x, for both of those, the amplitude is always the absolute value of that number up front. So in both of those cases, the amplitude would be, in one case it's the absolute value of 3, in the other case it's the absolute value of -3. Amplitude is 3. Simply meaning, from the origin, we have to go up 3 units, go down 3 units, and that's our highest and lowest point. Be careful, because some questions are worded, what's the difference between the highest and lowest point? And in that case, it would be 6 units, right? 3 above the origin, 3 below the origin. With me? So watch out. Read the questions carefully when dealing with amplitude. What does the negatives, these two graphs, guys, are not the same graph. Yeah, they do have the same amplitude. But what does the effect of the negative sign do out in front of the A value? It simply inverts the graph, as it does with all of the other cases that you had in the past couple of math courses with sticking a negative out in front. Compare, you all know what it's going to do here. Compare y equals x squared with y equals -x squared. What's the effect of the negative do? X squared, the parabola opens upward. -x squared, it opens downward. Compare y equals the square root of x with y equals opposite of square root of x. Put the negative out in front. What happens? It reflects it across the x-axis, which it did in our parabola problem. Same thing happens with the sine function. All it's going to do, and we'll do the sine of x first, and then we'll take a look at the opposite of sine x. And instead of the sine of 30 being positive 1/2, it's now going to say, okay, sine of 30 is 1/2. Oh, I want the opposite of. So it's taking whatever the point where it should be and reflecting it down across the x-axis. So high points become low points become high points, and x-intercepts stay the same, right? Because they're on the x-axis. So the first graph is sine of x, second graph is opposite of that, and you'll see the low points become high points and the high points become low points. You're just simply reflecting those across the x-axis. Okay? DNA. Now let's actually get to some questions here that you have to write some stuff. I'm never going to ask you to sketch graphs, pencil and paper. What I may ask you, or what the test will ask you coming up here in a couple of weeks, I might simply say, what's the amplitude of that graph? All right, I trust that you're going to be able to graph it and answer the graph questions by looking at your calculator. I'm going to be looking for what's amplitude, what's phase shift, are there any vertical or horizontal translations of the graph. Those you'll be able to answer here in a little bit. Okay, so we see what the effect of is by putting a value out in front or multiplying the trig function by a value. Let's start changing what we're taking the sine or cosine of. So So notice now that with sine x and sine of 2x, notice both of these have the same amplitude. Still a 1 out in front. Okay, that's not what we're changing now. That's what we changed up here. Go ahead and clear your two graphs out. Let's compare sine x with sine of 2x. We'll actually change what we're taking the sine of. Take a look at those two. See what you think. And then go back and change the 2x to a 4x. Sine of x. And then I'm going to go down here and graph the sine of 2x. And you know what else I'm going to do? I'm going to tell my calculator I only want to look at x values, x-axis. Let's define the x-axis to go only from negative 2 pi to positive 2 pi. And let's let the y scale, you all know that the amplitude is going to be 1, so we only have to worry about y. Let's just go from positive 2 to negative 2. So there's what I'm seeing, negative 2 pi to positive 2 pi. Now the first graph that you saw, right, I'll regraph them. I would regraph. The first one that you saw was y equals 2x. So you can see, right, from this point, from negative 2 pi to 0, well, that's a distance of 2 pi. So with sine x, just plain old sine x, it took us 2 pi radians to make a complete cycle. And then from 0 to 2 pi, it took us another 2 pi radians to make one complete cycle. So what do you notice with sine of 2x? How many cycles were completed in 2 pi radians? Or where is a complete cycle made? What's that?
Looks close to 2.5.
Looks close to. It looks like in 2 pi radians. From this point to this point, it looks like there's one cycle. There's 2 cycles. This looks like I've gone 2 cycles in 2 pi radians. Now, this value, what I'm slowly building, is eventually you're going to have 4 values that you need to concern yourself about. You will be able to take any trig function equation and think of it this way. And this also goes for cosine. I want you to start thinking of it as being a times the sine of b x plus or minus c. And then out here at the end we could also have plus or minus d. And it's the a, the b, and the c, and the d that's going to determine what in the world your graph's going to look like. We already talked about A. Changing A simply stretches the graph. We call that amplitude. Now we're talking about B, this number right here. B determines the period of your graph. Period means how many radians does it take to make one complete cycle. And the formula for period is 2 pi over B. You got to fill in the blank with B. And in our case, B is 2, right? In our case, B is 2. So what's 2 pi over 2? Pi. So according to what I'm seeing, it should take pi radians to complete one cycle. Is that what's happening with our graph? Absolutely. From this distance, from this point, negative 2 pi to 0, right? That's 2 pi. Well, where's half of that? Well, that's pi. It's right here. So is that the point where we've completed one cycle? Absolutely. So every pi radians, according to what I'm seeing right there, every pi radians, the graph completes a cycle. With me so far? So the period would be pi. How about the second one we wanted you to look at? Y equals 4x. Well, seeing what we just saw, our b value is 4. So therefore, period would equal 2 pi over 4. And that's the same thing as pi over 2. So what are we saying there? Every pi over 2 radians, you're going to complete one cycle. So leaving our window, negative 2 pi to positive 2 pi, if we go in here and change the sign of 2x to sine of 4x, here is pi over 2. Here's another pi over 2. Here's a third pi over 2. Here's a 4 pi over 2. And 4 pi over 2's, right, make 2 pi. So from negative 2 pi to 0, you're going to have 4 cycles. Okay? Making sense? All right. We've covered the A and the B. So what's left? Let's talk about the C and the D, and then we're pretty much done with what I need to get across to you today. Just simply their effects on the graph. This is a summary of what we just talked about. Just please know that 2 pi over b gives you the period of the graph, and that applies for both the sine and the cosine functions. Okay, we're going to worry about tangent another day. We're just going to focus on sine. Tangent's whacked. Tangent does not look anything like sine and cosine. It says here, sketch the graph of y. That I'm going to let you do in the sketching graphs. I'll leave it up to you. What I will ask you to do on the exam, however, would be what would be the amplitude. And now I can ask you what's the period of this graph. And you would say, well, the amplitude is the absolute value of negative 2, which is 2. So the highest point's positive 2, lowest point's negative 2. Also, I could ask what's the period, and then you would say, well, my b value is 3, so 2 pi over 3, or b, is 2 pi over 3. So every 2 pi over 3 radians, you'd have one of the cycles, whether it's sine or cosine. Now we're going to talk about translations, and what we mean by translations is how do I move the sine or the cosine graph? How do I move it left, right, up, or down? And I'm going to go back to college algebra with you for a second. You all remember that when you were asked to compare y equals x squared with y equals x squared minus 1, you all remember what the negative 1 does to the parabola, right? In that case, it moves everything down 1 unit, right? Y equals x squared is Joe Schmo average parabola. If you were to grab that parabola and move every point down 1 unit, it would look something like this. That's the effect of that negative 1. It simply takes this parabola and moves everything down 1. Had that been a plus 1, right, takes the parabola and moves everything up 1. So moving things up and down, really, really simple. You either add something to the end or subtract something from the end. You already know that. How do I move parabolas left or right? Who remembers? If I wanted to take y equals x squared, if I wanted to move that parabola to the right 2 units, what do I got to do? How would I write it? Not 2 times. 2 out in front of x squared will cause the parabola to become narrower, or in case of 1/2 x squared, make it wider. I think I got that right, yeah. How do I move the whole parabola 2 units to the right? Now I put in parentheses x plus 2, the quantity squared. Okay? And it was a little bit backwards than what you'd think. It makes sense that plus 2 moves up, minus 2 moves down. But when it's plus 2 inside the function, inside the square root, then it's going to actually move the parabola left 2 units, and x minus 2 quantity squared would move the x squared parabola right 2 units. And that's true for all functions. All functions. Had my original function been the square root of x, anybody remember what that one looks like? Kind of rough sketch like that. And if you want to move that whole function, move that whole graph to the left 2 units, you'd have to put the plus however many units I said, move it 3 units to the left. You got to put that plus 3 underneath the radical, and that would move the whole square root function to the left 3 units. Okay, you just need to understand that the huge difference between this and that. Where is the plus 3? Well, if it's outside of the function, that's how you move things up or down. So the one up top moves the square root of x graph up 3. When the plus 3 is inside the function, now you're, or whatever it is, you're moving things left or right, and in that case, you're going to move it 3 units to the left. The same principles apply to all of your trig functions, which is what you're about to see. Okay? Should have had that in college algebra. Now, when we move a graph, so periodic functions, when you and I take graphs and move them left and to the right, we call them phase shifts in trig classes. You know,